Okay, hello. Thank you for the opportunity to speak. Let me start off by asking one of the big questions in our field, which is that we've known for some time that planar n equals 4 super Yang-Mills theory is, quote, integrable. And I specifically put quotes around that word because I think the full extent of what exactly that implies, or for more complicated observables, is not completely understood. So what exactly would it mean to say that we have solved the theory, and when would we be content that we have a solution? Since super Yang-Mills theory is a unique theory, it stands to reason that there ought to be some set of principles, physical or mathematical or some combination thereof, that would, and the principles, a list of principles which would determine the sets of scattering amplitudes uniquely, since it is a unique theory. Now, for the moment, over the past many years, this is a question which has been addressed sort of experimentally by a number of different complementary approaches, some of which we've heard about in some of the talks here. Today, I'm going to be reviewing a series of papers by a number of co-authors. And the point of my talk today is to explain to you why we believe, or what the evidence is, for a deep connection between a branch of mathematics called cluster algebras and the scattering amplitudes of super Yang-Mills theory. So my talk will be kind of a broad overview of the flow of research that's gone through a number of papers. So the outline of my talk is, first I'm going to explain very briefly in simple words what is a cluster algebra. Then I'll review some of the evidence that we have that, which indicates that there is a deep connection between cluster algebras and the scattering amplitudes of super Yang-Mills theory. And then I'm going to turn the question around and ask, well, suppose we accept the hypothesis that there should be some connection. Can we use this knowledge to perform previously impossible calculations? And I should start at the outset by being very clear about what exactly I mean by cluster structure, since I'm not sure I've gotten this point across very clearly in all of these papers. And the answer is that I'm not exactly sure. This is, again, something that has to be discovered experimentally. I can show you several examples of amplitudes and what we mean when we say that they have cluster structure. But ultimately, the final story is yet to be written, and the full connection between scattering amplitudes and cluster algebras is not yet known. Okay, so let's just jump right in, and let's look at the simplest non-trivial example of a cluster algebra. This one is called the A2 cluster algebra, for a reason you'll see in just a moment. The idea is very simple. Let's say you start with some two-dimensional manifold with a Poisson structure, and you have two functions on it. Let me call them x1 and x2. And your two functions are log canonical with respect to the Poisson bracket. And when I use that phrase, what I mean is that they satisfy this equation shown here, that the Poisson bracket between log of x1 and log of x2 is equal to 1. And we can choose these functions to be the coordinates on our manifold, so I'll go ahead and call these two x's the coordinates. Now there's something really neat that given two such functions, x1 and x2, there's actually a very simple transformation rule which lets you generate new pairs of log canonical coordinates. If you replace x1 and x2 by, well, the next successive pair would be x2 and 1 plus x2. Oh, there's a typo. I'm sorry. That should just be x1. The next pair is x2 and 1 plus x2 over x1. You can check that that pair, again, is log canonical with respect to the Poisson bracket. And you can continue iterating through this sequence. Again, if you delete that 1 plus at the bottom, I apologize for that, you can generate additional pairs of log canonical coordinates on your manifold. Now, an interesting thing, which is not at all obvious, at least to me, from this relation here, is that it's periodic with period 5. So you start with x1, and then, so the first pair you start with is x1, x2. Then the next pair you get is x2, comma 1 plus x2 over x1. And then you keep iterating this recursion. By the time you come around to the fifth element, you come back where you started. Okay. So the 5xi, so let me be clear, I'm calling this one x1, x2, x3, x4, and x5. They're all, these are 5 different functions, but on a 2-dimensional manner. So of course they're not algebraically independent, but I give them 5 different names because there are 5 of them. These 5 xi constitute what we call cluster coordinates on the A2 cluster algebra. And now I can finally reveal why it's called the A2 cluster algebra, because we represent this Poisson bracket by a quiver, where you draw one node for each cluster coordinate, and you connect an arrow from node I to node j the number of times is given by the Poisson bracket. So here, the Poisson bracket between log x2, log x1, and log x2 is 1. So I connect node x1 to x2 with a single arrow. And that, of course, resembles the Dinkin diagram for A2. So more generally, and this is a beautiful piece of mathematics that was discovered by Falk and Goncharov, a cluster on a cluster Poisson variety of dimension d is given by a collection of d log canonical coordinates. And here, more generally, when I speak of log canonical coordinates, I just mean that you have a collection of coordinates such that the Poisson bracket of the log of xi with log of xj is some integer. Of course, this has to be an antisymmetric matrix of integers. And we can represent this by a quiver where you draw one node for each x, and the number of arrows directed from vertex I to vertex j is equal to bij. Okay. And there's a simple operation, the operation which generalizes this kind of transformation. There's a simple operation called a mutation on xj, which, given a collection of coordinates in some cluster, you apply that operation, and it generates for you a new set of coordinates. There may be some overlap between the new and the old cluster, but in principle, it generates a new set of coordinates via this formula here. So in totality, the cluster algebra associated to this Poisson variety, whatever the one is that we happen to be considering, is generated by the union of all cluster coordinates that you can possibly generate through any sequence of mutations. So in the A2 example that I just showed a few moments ago, we saw that the mutation is actually periodic with period 5. So you only generate 5 different clusters. And in fact, you only generate 5 distinct cluster coordinates. So the first cluster has these 2 coordinates. The next cluster has those 2 coordinates. The third cluster has those 2 coordinates, etc. You have 5 different clusters with 5 distinct coordinates. In general, depending on what kind of quiver you start with, this operation may or may not terminate. Well, it's known that there's a known classification in the mathematics literature, which is that this operation does terminate, giving you a finite number of cluster coordinates if and only if the quiver that you start with is mutation equivalent to the Dinkin diagram of one of the classical Lie groups. Okay. But anyway, this is the definition of cluster algebra. Now this might seem a little bit abstract. Where am I going with this? Where on earth is there a cluster Poisson variety hiding in n equals 4 super Yang-Mills theory? Well, it's nothing mysterious. It's hiding just in plain sight, really. Let's just ask the very simple question, what is an n-particle amplitude actually a function of in n equals 4 super Yang-Mills theory? Well, we're scattering n massless particles. Each massless particle corresponds to some null vector in Minkowski spacetime. Of course, we have total momentum conservation, so the null momenta sum up to 0. They form a closed polygon if you put them back to back. And we know from the work of Hodges that there's a nice parametrization. Of a collection of n ordered null momenta in terms of momentum twisters. And let me add, I mentioned at the very beginning, but my momenta have a natural ordering because when you work in the planar limit, there's a natural ordering associated to these particles which lie in the adjoint of your gauge group. Okay, now then we have an additional fact, which is a very special property of super Yang-Mills theory. There are some other field theories in other dimensions that have this as well, but in 4 dimensions, a special property of super Yang-Mills theory is what we call dual conformal symmetry. And in this parametrization, if I view, so this is now a 4 by n matrix. So each column here is a 4-component homogeneous coordinate on P3. And in this parametrization of the massless kinematics, dual conformal transformations correspond to multiplication from the left by SL4. So in n equals 4 super Yang-Mills theory, amplitudes are actually functions on the quotient space. And the quotient space, when you take this, the space of 4 by n matrices like this, where each column is interpreted as a homogeneous coordinate in P3, that's a quotient of the, you can realize that as a quotient of the Grassmannian. We call that conf n P3, which is read as configurations of endpoints in P3. And this manifold is well known to mathematicians, and it has the structure of a cluster Poisson variety. So this is the cluster Poisson variety that underlies n equals 4 super Yang-Mills theory. So again, to recap, it's nothing mysterious. It is literally the kinematic manifold on which amplitudes live. The manifold that they are functions of has the structure, has a natural cluster structure. So let's look at a simple example to get our bearing. If we look at 6-particle scattering, the space of kinematic configurations modulo dual conformal invariance is 3-dimensional. In general, it's 3n minus 15 if you have n particles, because here you have each one is a coordinate in P3, so each column has 3 independent components, and then you're modding out by SL4. So 3n minus 15. For n equals 6, we have a 3-dimensional manifold. So let me go ahead and choose some coordinates on this manifold. Now, there's a common choice in the literature when people have looked at 6-particle amplitudes. They use certain cross ratios called U1, U2, and U3. But I'm going to make a better choice in this talk. I'm going to choose coordinates x1, x2, and x3, which are non-trivially related to the U's if you happen to be an expert in 6-particle amplitudes. But I've chosen these because these have a canonically normalized Poisson bracket. So the notation here is that each of these 4 brackets is a Plucker coordinate. So you take 4 of the column vectors and put them next to each other and take a determinant. So each of these are perfectly fine coordinates on my quotient space because each particle label appears the same number of times upstairs as downstairs, so they're invariant under rescaling. And I've chosen these so that they have, as I said, a nice Poisson bracket with respect to the canonical Poisson structure on this manifold. So in particular, you can just sit down and calculate that the Poisson bracket of the log of x2 with log of x1 with x2 is 1. The Poisson bracket of log of x2 with log of x3 is 1. And log of x1 and log of x3 Poisson commute. So there are 0 arrows from x1 to x3. So these 3 coordinates constitute a cluster of what we call the A3 cluster algebra. Again, A3 because it's the Dinkin diagram of A3. Now you can start applying the mutation algorithm, and it's quite beautiful. It turns out there are 14 distinct clusters, and there are a total of 15 distinct cluster coordinates that you'll encounter as you traverse all the possible clusters. And here are a list of the other 12. Actually, there's a cute list of cluster coordinates on the Wikipedia page, but you should beware if you look at it, because the variables listed there, even though they're called x1, x2, and x3, to confuse you, they refer to a different type of cluster coordinates called A coordinates. Now, if you prefer, you can go back and rewrite all of these coordinates in terms of the Plucker coordinates if you wish. So depending on what kind of calculation you're doing, it may be more useful to leave them like this. This has the advantage that when you work with these x coordinates, you have functions which are manifestly positive everywhere within the positive domain. So as long as x1, x2, and x3 are positive, it's manifest that these are all positive as well. But sometimes it's more convenient to work in the Plucker basis, where you can re-express these in this form. A point which will be important momentarily is that only 15 of the possible cross ratios that you can write down are cluster coordinates. There are plenty of other cross ratios you can write down that are not on this list, and that are not cluster coordinates. So we need to look at some experimental data to see the utility of these coordinates. So let's take a look at the two-loop six-particle MHV amplitude. And it can be written in a pretty nice form like this in terms of the classical polylogarithm functions. And one thing you can observe is that the argument of every polylogarithm is a cluster coordinate. You never get a cross ratio that's not a cluster coordinate, nor do you get some arbitrary function of cross ratios. So when you start digging into the literature and you look at some of the heroic calculations people have done, you can very quickly get overwhelmed with Mathematica packages that have hundreds or thousands or tens of thousands of terms. So just to give you a flavor for where I'm headed with this, let me give you a quiz. Suppose I'm just going to assert that if you were to take a look at two-loop MHV amplitudes, you're only going to see certain cross ratios and not other ones. So here I haven't yet defined all the notation here. I haven't defined these caps. But don't worry about that for the moment. Let me just ask you, when you're scanning through these hundreds or thousands of terms, if you didn't know anything else, you would have no idea whether to expect that any one of these cross ratios is better than any other one. But I assert that it is a fact that as long as you're looking at two-loop MHV amplitudes, you'll never see cross ratios of the type R2 or R3. You'll only see type R1, and we know that because that's the one. We know that because experimentally we look at the calculations and observe it's the only one there. And the explanation for it, the posteriori explanation, is that that's the only one that's a cluster coordinate. So I just need to 2 slides to review a tiny bit of additional mathematics which you need to make more precise statements for more general scattering amplitudes. A large class of amplitudes can be expressed in terms of what are called generalized polylogarithm functions that are graded by their weight. So this is the same as the weight of an ordinary polylogarithm function Lik. So an operational definition of a weight k function is that its differential is a linear combination of functions of weight 1 less times d log Ri, where the Ri are rational functions. Rational functions of what? In practice, I mean rational functions of the cluster coordinates. And so by iterating, you can take the differential of the differentials, etc., until finally you collapse your function down into a bunch of functions of weight 0, aka rational numbers. So we assemble this into what we call the symbol of the function, which is this collection of rational numbers, and then a tensor product of these rational functions. So if you hand me some amplitude or some generalized polylogarithm function of this type, the set of all allowed rational functions that can appear here in its symbol is what we call the symbol alphabet. Okay, so observation number 1, and this is an observation that's supported by all, quote, experimental evidence to date, by which I mean heroic computations that have been undertaken by many groups, support the hypothesis here in the box, which is that the cluster coordinates on the GR4n cluster algebra, remember that's the one relevant, that's the Poisson variety hiding inside n equals 2 super Yang-Mills theory, they provide a basis for the symbol alphabet of all n-particle amplitudes. At least, and then the parenthetical comment here is, at least all of the ones which are of generalized polylogarithm type. This is a little bit of rampant speculation, but it might be possible to remove that parenthetical comment. So let me just explain briefly. For n greater than or equal to 8, this cluster algebra has infinitely many cluster coordinates. The mutation process doesn't close. Of course, only finitely many of them are needed if you have a generalized polylogarithm type amplitude at any finite loop order. However, for n greater than or equal to 10, and we might hear about this in the next talk, there are certain amplitudes which certainly cannot be expressed in this generalized polylogarithm type. Now, this represents a new frontier in amplitudology, and very little is known explicitly about these type of functions. But there are a few instances in scalar theory, not super Yang-Mills, where such elliptic integrals have been evaluated explicitly. And in the cases that they've been looked at, they can be written as infinite sums of polylogs. So it would seem too much of a coincidence that mathematics gives us an infinite set of cluster coordinates exactly where we need them. So it is possible that the principal symbol alphabet equals cluster coordinates might extend to all amplitudes, even the elliptic ones and higher, once you properly interpret both sides of this equation to allow infinitely many symbol letters and infinitely long linear combinations of polylogs. Anyway, that's rampant speculation. But let me mention another manifestation of the cluster structure that we've observed. And this is for two-loop MHV amplitudes, where we have a lot more data thanks to a calculation in 2011 by Caron-Huot. So what we've observed by data mining his result is that the co-bracket, and I'm afraid I really don't have time to define the co-bracket for polylogarithm functions. They constitute elements of a Hopf algebra, so there's a natural coproduct on it. But what we've observed by data mining his results is that the co-bracket of any two-loop MHV amplitude can be written in a very specific form. It has a 2, 2 component and a 3, 1 component, each of which can be expressed as linear combinations of the classical functions with cluster coordinates obeying only very particular Poisson bracket. So you never have just completely random functions appearing in these co-brackets. It's always linear combinations of functions with either Poisson bracket 0 in this component or 1 in this component. And this is a very rare thing. One of the things we've been exploring in our papers is, suppose you didn't know anything about amplitudes, you just study mathematically the collection of all functions that can be written in some symbol alphabet. And you can ask, how special is this property? Is it, how constraining is it? And I'll get to that in a second. That motivates, in fact, what we call the cluster bootstrap. We still have no idea why these properties hold, but we can turn things around and ask, suppose we adopt the hypothesis that there should be some kind of cluster structure. Can we carry out new, previously impossible calculations? So one application is, suppose we knew nothing more about the two-loop MHV amplitudes other than some very simple physical constraints. They must have consistent collinear limits, physical branch cuts, dihedral invariance because of the Bose symmetry, and there's a certain condition on their differential due to supersymmetry. But suppose someone hands you, in addition to that collection of physical constraints, apparently out of nowhere, a mathematical constraint, and they tell you, oh, I know that the amplitudes have to have this particular cluster structure. Well, then it turns out, and this was something we published last November, these properties completely determine the MHV two-loop amplitudes modulo terms which are products of functions of lower weight. And now for n equals 6 and 7, I actually know that you can eliminate that proviso entirely. I suspect you can eliminate it for higher n as well, but the computations become extremely difficult. Basically, you're working with an extremely large function space, and you're trying to show that the only linear combination in that function space that satisfies the criteria you impose is a unique one. But the function spaces get big very quickly, so it's a tedious calculation. Another application of a kind of cluster bootstrap that we did last December is to look at the symbol of the 3-loop 7-particle MHV amplitude. And this was rather surprising because, so we made the following ansatz, that it should be a weight 6 generalized polylogarithm function whose symbol alphabet is the set of cluster coordinates for GR4, 7. Its cluster algebra has a cluster whose quiver is isomorphic to E6, so it's called the E6 cluster algebra. And then you impose that it should only have physical branch cuts, satisfy the SUSY condition, and that it should be finite and well-defined in the collinear limit. These simple properties uniquely fix the symbol of that amplitude. So this is an example of a general phenomenon that we're slowly uncovering experimentally, which suggests that there's a sense in which these functions, the scattering amplitudes of Super-Yang-Mills theory, barely exist given all the constraints that they satisfy, both physically and mathematically. So what we've been exploring recently is the power of the cluster bootstrap employing the cluster structure and the collinear limits. And it seems that the power comes from the fact that the cluster structure and collinear limits are almost completely orthogonal to each other. So finding a set of functions which satisfies both is extremely constraining. If you imagine this red squiggly thing is denoting the set of all possible hexagon functions, that is, all possible functions which could conceivably appear in any 6-point amplitude. Well, a generic function in this set is not the collinear limit of any valid 7-particle cluster function. The valid 7-particle cluster functions, when you take their collinear limits, they span only a subset of all hexagon functions. And similarly, you can iterate upward. An actual 6-particle amplitude has to sit at the base of this infinite tower of collinear limits, where you have higher and higher cluster constraints as you go up to higher number of particles. So the yellow that you can barely see are all possible 9-particle functions, and the green are all possible 10-particle functions, etc. So there's a very delicate set of constraints between the cluster constraints and the collinear constraints that we've been exploring. So in conclusion, in my talk, I've reviewed very briefly what is a cluster algebra. I've provided you some evidence for the fact that amplitudes in Super-Yang-Mills theory exhibit some deep connection with cluster algebras. We don't know the full extent of that connection. And I've showed you that we're also exploring to what extent they may be actually determined by the cluster structure, or the cluster structure plus simple physical constraints. And the answer is that in the cases we've looked at, the cluster structure is highly constraining. So in conclusion, evidently cluster algebras are part of the language in which Super-Yang-Mills theory amplitudes want to be written. The scattering amplitude functions barely exist, so a mathematician might be curious to ask, what is the precise mathematical question to which the set of scattering amplitudes in n equals 4 Yang-Mills theory is the unique solution? Again, since the theory is unique. And since reformulating is the name of the game these days, it's tempting to wonder whether there's an alternative formulation of Super-Yang-Mills theory in which these, and I have to admit, they're very physically mysterious, the physically mysterious cluster properties, and in particular, the extremely mysterious relation to the Poisson structure. It's almost like it's begging for you to quantize the kinematic space somehow. Is there an alternative formulation of Super-Yang-Mills theory that makes these properties manifest? So, thank you.
Okay, questions?
In the non-planar case, there is no connection to cluster algebra?
Apparently not, though, as you know, this is an experimental science. So, one of the problems is that in the, well, yeah, let me not say more. We could discuss that privately.
Eva?
Is there a cluster structure at NMHV?
Yes, absolutely. So, this fact, this fact that the symbol alphabet is the set of cluster coordinates, that holds true for any amplitude, NMHV, non-MHV. This particular statement here, so again, this is why we still have to explore experimentally which kinds of amplitudes have which structure. It was great that Simon gave us the all n MHV at once, because then you can look at the whole family and make a statement. For NMHV, there's precious little data in the literature, and if you look at 6- and 7-point amplitudes, NMHV, they don't satisfy this, or at least they don't obviously satisfy this, but there's several R components, there may be particular linear combinations that have cluster structure. Until we really know all n results, we might not know exactly how to generalize this kind of statement. Or it could be that the right way to think about it is in terms of cluster superalgebras.
Come on.
So my question is about the Poisson structure that you mentioned, which is mysterious still. So since you're identifying the CP3 with momenta or coordinates characterizing the momenta, non-commutativity on that space must mean non-commutativity of momenta.
Yeah.
So it's natural to ask if non-commutative Yang-Mills gives rise to
That's an excellent question.
Has nobody asked that question?
No, I don't think, no.
Any other questions? I think I had a quick one. So you mentioned the relationship to classification of Dynkin diagrams.
Yeah.
So is the number of cluster coordinates you get, is that related to something in the Dynkin diagram, the dimension of representation, anything?
No, nothing simple.
Nothing simple.
Yeah.
Right, let's thank Marcus again then.